Okay, and welcome back to one more video in Unit 11. Alright, the rest of this chapter is going to be basically equilibrium type questions. A lot of calorimetry, wow, that's a hard word to say, and equilibrium questions. So what does it mean to be in equilibrium? I guess that's what we should answer first. Well, let's take a look at my cup of coffee right here. Now, I've got this little metal weight, and I'm going to drop it into my coffee. Well, not really, because I want to keep drinking this cup of coffee. But anyway, what would happen? Here I've got this piece of metal, my hot cup of coffee. What's going to happen when I put these two in contact with each other? Well, obviously, the coffee is going to heat up the piece of metal. The metal's probably even going to cool my coffee off a little. The big idea is this: when you put two metals or two objects in contact, they're going to I'm not going to say going to, but I'm going to say they should reach equilibrium with each other, which means the temperature final for this piece of metal and the temperature final for this cup of coffee should be the same temperature. So really what I'm saying is this: if I should tell you that something gets to equilibrium, I'm trying to tell you that the temperature final for every material is the same temperature final. At least that's what I'm trying to get at. So this is going to bring me up to these calorimetry type questions. And a calorimetry question, what I'm saying is everything has an MC delta T. This piece of metal has an MC delta T. My cup of coffee has an MC delta T. So every object has an MC delta T. But here's the thing. For the heat that this cup of coffee loses, this piece of metal should gain. So the thing is, heat is not created or destroyed. Remember the whole conservation of energy thing. So I'm not losing heat, I'm not gaining heat, I'm just transferring heat. So the idea, the foundation in every one of these problems is this: the sum of all my MC delta T's should be equal to 0. The heat one object loses, another object gains. So like in this problem, I should have two Q's. I will have a Q for my coffee, and I know it seems odd to write it like that, but I will. I will have a Q for my coffee. And I would also have to represent a Q for this. Matter of fact, I think this is a piece of zinc that I keep holding. So I would have a Q for this piece of zinc. And whatever this is, whatever my coffee loses, my zinc gains. And I know that it's not created or destroyed, so it's equal to 0. This is the foundation for every single problem we're pretty much working right now, is that the heat is not created, it's not destroyed, it's conserved in the process. So that's where we're at this point. Now here's the thing. I could even try and include this coffee cup in there with it. So I could write another Q for my plastic cup in here, because everything has a Q. The coffee would have a specific heat. So there would be a C for the coffee. The zinc has a specific heat. Everything has a specific heat. So if you're asking, okay, so what is a calorimetry? You're going to see the word calorimeter in a lot of these problems. Let's crank this camera back. I'll probably never get focused again. But this silver object is a calorimeter. And if you take a little look at here, you can see there's a thermometer stuck out of the top of the lid. And usually what happens when you're doing a lab, if you hadn't done one, there's an inner cup to this thing. Here's the inner cup. And it's trying to be like an insulator. I'm trying to tilt this back and do it all one-handed. It's actually pretty hard. I'll put it back together. And you'll put some water down inside here. And then usually you cap it back off. And what you'll be doing is heating this piece of metal up at the same time. And pretty much everybody heats this metal up in boiling water is what will happen. That way you know the temperature of this metal. And what will happen is this. Somebody will take the lid off the calorimeter, you'll take this hot piece of metal, and then you'll drop it or set it down in the water, cap it back off. Well, what's going to happen to the temperature of this thermometer? Well, the hot piece of metal is going to meet the cold water, and they're going to exchange heat, and in the end they'll reach equilibrium. The thermometer should rise just a little bit, and the temperature will go up. So that's where we're looking at in this problem. So I'm going to try and see if I can get this camera back into a situation and we can work again. Alright, so I think we're in good shape. Can everybody see that? Okay, what am I saying? You're on YouTube. You can't answer me right now. Anyway, so let's take a look at this. What if we were doing a problem, and let's draw this little calorimeter. So here's a calorimeter. Here's the inside of it. And every one of those problems is going to have the same premise. We're going to have water inside that calorimeter, some good old H2O. And the reason why we love doing these problems with water is because we know that C for water is either 4,186, 4.186, or it is 1. One of these three. Now, of course, you need to always make sure you've got your units. 4,186 would be for joules and kilograms. 4.186 would be for joules and grams. And 1 would be for calories and grams. So you've got to always make sure you know what units you're going to work the problem in. So anyway, you do this water, and you'll get a temperature for this water, and then somewhere off to the side, here, let's draw us a hunk of metal right here. So there's my hunk of metal, and someone is going to get this piece of metal hot. Bah! Put the fire on it. So they get this piece of metal hot, and then what they're going to do is take this piece of metal, and they're going to put it into the water. So here is my supposed piece of metal in the water. Well, what's going to happen? The metal's going to lose energy. The water's going to gain energy. So the final temperature, the metal should cool off. The water should heat up. So if I was doing this problem, what would the physics look like in this problem? Well, let's do a sum of the Q's. Sum of the Q's for this question would be, I'm going to have a Q for the water plus a Q for the metal. I'm going to set all equal to 0. And that's literally, the physics in this problem is done. Now, if the problem wanted to be nitpicky about it, this is the inside. This is that inner cup of the calorimeter. It might give you a mass. It might give you a mass for this. Well, that's no problem. This thing's made out of aluminum. So, what if it did? Well, I would write Q for water, plus I would have a Q for the metal, plus I would have a Q for the aluminum, and I'd still set it all equal to 0. All right, so now you're probably asking, so what does all this mean in terms of working the problem? Well, let's take it a step farther. What would the equation look like for this? Well, the equation would look like this. Let's see what we can do here. We said we'd have a Q for water. See if I can straighten this out. We said we'd have a Q for the metal and a Q for the aluminum. Heck, there could be glass in there too. Who knows? Wow, there's a choir down the hall. That's something I don't get every day. Anyway, so what would the equation look like? Well, you see, every one of these is an MC delta T. So what I'm going to do is I need to write an MC delta T for this one, an MC delta T for this one, and an MC delta T for that one. So I'm going to come back in here, and now let's write this out. I would have an M water, C water, TF minus TI water, plus, now, I know you're looking at this and you're going, hey, you forgot to put a W at F. You put a W on everything, but you forgot F. You're right. I know I forgot to. I'm intentionally not doing it. So now I'm going to come back. I'm going to put an MM, a CM, TF minus TIM. Lindsay, would you shut my door before I bite the head off of some kid? Plus, I need to do one more. I need one more. I've got all this. Now notice again, I forgot to put an M. Or did I forget to put an M here? Well, let's do one more. Let's do one for the aluminum. So plus an M for aluminum, C for aluminum, and then TF minus TI aluminum. And I set it all equals 0. I know it looks like this huge equation. The thing is, these problems are not hard. They're very generic and easy problems. And Lindsay, if you want to make a copy of those, feel free to just go make a copy of the answers. I don't care. That way you ain't got to look at them. Okay. So, anyway, if you're still wondering, why did I leave every one of these alone? Alone. I left you alone. Why? Because the TF is the same for every object in an equilibrium. I could have Q plus Q plus Q plus Q plus Q. Are you getting the point? The thing is, the temperature final for every single object in this is the same temperature final. So there's no, and most of your problems aren't going to get over like 4 things in there. But anyway, let's do an example and finish this video. You've actually learned everything you need. at this point, the only thing you've got to do is just do a problem. So here you've got a problem, and I'll do my famous calorimeter drawing in here. And in this problem, we've got a calorimeter. There's my calorimeter. Let's put some water in there. Get this blue one out. So here's some water. And as a matter of fact, it tells me that there's 0.4 kilograms of water. And then it also tells me there's an ingot of metal. So here's my ingot of metal. I'll put a little hook on it because that's pretty common. And it says that the ingot is 0.05 kilograms. So there's my hunk of metal. Here's my water. Now it tells me something else. It tells me that the metal is heated to 200 degrees Celsius. So there's the temperature of the metal. It tells me that the water is a nice cool 20 degrees Celsius. And it says somebody drops the metal into the water. Well, what do you expect is going to happen? The metal is going to cool off. The water is going to heat up. And it says that the temperature of the system, mixed system, is 22.4 degrees Celsius. So what does all this mean? Well, this is my temperature final. The 200 degrees is my, I'm going to call it TEMA. That is my temperature initial of my metal. And this 20 degrees Celsius, that is my temperature initial of water that I've got in this. So this problem says it's dropped in a beaker. And I'm going to assume I can ignore it because I want to know, is this a glass beaker? And if so, how heavy is it? But apparently I get to ignore that in this problem. So my equation is going to look like this. I'm going to have a Q for the metal and a Q for the water. So what would you do if this glass beaker had a mass in here? Well, I'd write plus Q for the glass equals 0. It wouldn't be that big of a deal. Now I'm going to break my equation down. The physics is over. Now all I got to do is break this down. That would be MM, CM, TF minus TIM plus MW, CW, TF minus TIW, set it all equal to 0. And now all this is going to be is me filling numbers into this equation. It told me that the metal has a mass of 0.05. Now, it's actually wanting me to find the C for the metal, so that I do not know. Temperature final. It told me that my temperature final is 22.4 minus my temperature initial of metal, which was 200 degrees, which is obviously very hot, plus mass of water, 0.4. Now, notice something. I'm in kilograms. So what am I going to use for my specific heat? Well, I'm going to use 4,186 because that is C for water in kilograms. And then I've got temperature final, which is 22.4 minus temperature initial of the water, which it said was 20. Well, now let's plug all this into a calculator. And believe it or not, it's a shame when people get to this point and miss these problems, because that's horrible. Shame on you. You've already done all the work. Now just don't mess anything up. So what we got here, I've got 22. I'm going to put in parentheses 22.4 minus 200 times 0.05. 0.05 equals, I've got negative 8.88. So I've got negative 8.88 cm. So I've got this, and that's what everybody does. They screw this up in the calculator. Take this difference and then multiply it. Now come over here. This I can put in my calculator all at once. Let's see, 0.4 times 4186 times, I'm going to put in parentheses though, 22.4 minus 20, although that is 2.4, so I feel kind of silly for having just typed that in a calculator. Anyway, equals 4,019, so plus 4,019 equals 0, so this ends up being 4,019 equals 8.88 cm, and I'm almost there. 4,019 divided by 8.88 is equal to 453 And I did this problem in joules and kilograms. Joules per kilogram Celsius degree. And I am done with this question. By the way, most of these problems ask the same thing. Most of the problems are either going to ask you to find, like this, C for metal. They're going to ask you to find the mass for a metal. In other words, it'll tell you it's a piece of silver. Well, if it tells you it's silver, you'll know what C is. I guess the hardest ones ask you TF. And if it asks you TF, you got to notice how you've got more than one TF. That means you've got to distribute everything in the problem if it asks you for TF. You guys distribute, combine your like terms, and so forth. And if I need to work one like that, I will. But anyway, thank you for watching. Bye-bye.